will begin. This is exercise 1I. Remember, 2 exercises per week. So again, the next session you have time to digest this information before we go into the next one. The next exercise is the second method of simultaneous equations. There's one part of it that mainstream Year 9s normally learn the technique, so they just know the technique, but then to understand why the technique works and what is it used for is what I'm going to try to explain today. Okay? So, one of the first techniques, which is, to me, the easiest way to understand it, and the easiest, not the easiest way to do it, but it is the easiest to understand how to do it. Okay? Now, when two straight lines are drawn, how many possibilities of intersection can you expect if they were to intersect? If I drew two straight lines, and they did intersect, how many intersections can you expect? There's only one, logically. And at this Year 9, Year 10 level, you normally only work with straight lines. But it doesn't mean that every simultaneous equation you do from here on is always going to be one. You can do a straight line with a quadratic, which is a parabola, then it will have two. You can do a straight line that intersects with a sine graph that has pretty much 3, 4, maybe even 6, depending on the angle of a straight line. The techniques are exactly the same, but the meaning is different each time you do. So to start off with, we usually do straight lines because it's the easiest to understand. So straight lines right down here, you can only expect one intersection. And so, what can you expect? There's one, and so therefore there are 3 possibilities that can occur with 2 straight lines, which I've kind of slightly touched on in our last session when I talked about parallels and perpendicular lines, because these 2 exercises essentially tie into each other. And the first chapter 2, 2F of Year 11 methods, this is where students need to then think hypothetically. So I'll show you what I mean soon. So you get 2 straight lines. When they call it a unique solution, what they're really saying is there is only one intersection for 2 straight lines. That will occur when it looks something like this. Now you learnt kind of the logic last session where we talked about parallel, perpendicular. What do we know about these 2 straight lines? In order for you to have one point of intersection, what must occur between these 2 lines? Anyone remember? So there's a y equals mx plus c. Let's call it y1. And the other one is y2. And it's a y equals mx plus c. What do we know? What must occur for one solution to even happen? What's the first thing you got to look for? Well, that's true. If m1 times m2 equals -1, what does that tell us, though? That's true. I see what you're thinking. What does it tell us if it's actually that property? If m1 times m2 is equal to -1, it is perpendicular, which also happens to be that it does intersect as well. So that's true, but not all lines have to be perpendicular, right? They can be very thin and they still intersect, but it doesn't have to intersect at 90 degrees. So that is not truly that property. What's another thing that you can think of?
If they have different gradients and different rules.
Very good. Now, when you said different gradients, what you're saying here, and that ties back to what Una was sort of hinting out here, M1 and M2, so I'm going to call this M1, this is M2, you just need to make sure that M1 and M2 does not equal. As long as they're not equal, they're not parallel. Because if they're parallel, then they'll never intersect. So as long as M1 does not equal to M2, it will always guarantee you will get a unique solution. This is what the Year 11 methods students will then start to explore, which I'll show you soon. No solutions. What does that mean then? How is it possible to have no intersections? Someone just said over here. Samuel.
They have the same gradient.
They have the same gradient, means they are parallel. So the second possibility is that you can have 2 straight lines that do not intersect at all. So hence, like Samuel said, gradient 1 has to equal to gradient 2 in order for that to occur. So in one scenario, if they're equal, well, they're going to be parallel. In the other scenario, if they're not equal, well, they're definitely going to intersect. And because they're both straight lines, we know there's going to be one point of intersection. What about the third one? When we say infinite solutions, that means there are infinitely many intersections. How's that possible? We said there's only one intersection. How is it possible to have infinite intersections? That's right. Because if you have two of exactly the same lines when I type them, they're pretty much intersect at every single point. So the logic here is then, well, that means both M1 must equal to M2 and C1 must equal to C2 for you to have infinitely many intersections because you essentially have the same group. That implies, and this is what makes the year 11 methods when they first come in, what makes this exercise a bit tricky, because what's common about no solution, infinitely many solutions? What's common there? They have the same gradient. And at their level, what they need to test is that they'll have a question where it could be something like this. I'm just going to write this, don't copy it down. They'll have something like y equals to m minus 1 x plus, I don't know, let's say m, hypothetically. And then they'll say, for what values of m, so you've got to come up with a number for m or multiple numbers of m, such that there will be no solutions. And so what numbers of m, if I had to sub it in now, can m be 1? And we'll have no solutions with a second equation. Let's say, I don't know, I'm just going to make it up now. So if I wanted this one to ensure that there's no solutions, what numbers of m would ensure that that will happen, hypothetically? Yeah? This one will be easier to do because I gave you extra numbers. And what they'll do is they'll have to test that m1 equals m2, but then actually ends up being two scenarios. You need to make sure just because the gradients are the same doesn't mean that they're parallel. It also means that they might be the same line. So then you have to test if the y-intercepts are the same as well. So it means, just to add on another condition then, that means for it to be parallel, you've got to write this extra one. C1 cannot equal to C2. Because if they have the same y-intercept, then they're just going to be the same line. So if you want them to be parallel, you've got to make sure y-intercept does not equal. Then the last condition, just to fill in things, so this one has M1, M2, this has C1, C2, this one has M1, M2, this has C1, C2. What do you think the condition is if it's unique solution? Doesn't matter. That's right. And so at your level, we don't use set notations yet, so we don't say C is an element of real numbers. That's normally how we say it. For your level, we'll say C can be any number. So it doesn't matter. And that's the property, that's the first introduction of simultaneous equations for the year 11 methods, if you want to look at it at an extension level. But for your level today, I'm only going to teach you, well, how do you find it if there is an intersection? Which means this point. There's two methods, and the two most popular methods in year 9 mainstream is you learn substitution method, the next one's called elimination. So that's what we're learning today, okay? All right, so that's the theoretical part. Let's do the logic on how. So for simultaneous equations, we are focusing on unique solutions. So I'm talking about this one right here. We need M1 and M2 not to equal, and C can be any number, and then we can then solve it. So if you look at any of the equations, if it ends up being that the gradients are the same, you won't be able to solve it. It's just impossible to solve, okay? Here we go. For simultaneous equations, we're focusing on unique solution, meaning when two lines, and I want you to write here so that you know, intersect. When they say do simultaneous equations, what they're really implicitly saying is find the intersections. Okay, that's what they're saying. So it doesn't have to be straight lines. It could actually be a straight line with a curve, or it could actually be a curve with another curve, and you're going to find the intersections of those 2 points. And we call that simultaneous equations. Okay. The logic to this method, which is the first method I'm teaching you, this shape is called a cubic, which you'll learn that's an x cubed graph. An x squared graph will look like that, and your x to the power of 1 is a straight line. Yeah. So once you learn pretty much these three in year 11, you can then do x4, x5, x6 all the way x99. But each one is a chapter to learn. Okay. Say it again. Actually, there's a pattern. Actually, this might be a bit off chart here. I'm going to pause the video. Out of curiosity, let's see. And it's recording. So ignore what I said before. It was just something I thought I only do this with you guys because I think you guys, one, you are attentive and you can do a bit of thinking about it. Normally, I don't try to do that. Otherwise, it confuses a lot of students. So let's look at the point of intersection. The coordinates are, and I want you to write this down. the coordinates are equal for both equations. What am I saying? I'm saying when you get equation 1, y1 equals m1x plus c1, right? When it intersects with another line, call it y2, what we know is that the gradients have to be different in order for them to intersect. But not only that, we also know another thing. We know that if they did intersect, the point of intersection is an x and a y coordinate, right? And this is key. This is powerful because that's where the theory comes in, and why elimination method works and why substitution method works, is because both lines, even though they have different equations, we know that at this one point, and only that one point, where both x coordinates are the same. So if this point here was 1, 3, for example, it means that you can sub 1 into equation 1, and the result should be 3 for equation 1. And if you sub 1 into equation 2, it should also be 3 as well. Because the rule says that even though the rules are different, they're only the same right there. Because they have to have the same x and y coordinates, right? So whatever the rule is, if you put x equals 1, both the y values have to be the same. That's what I'm trying to say here. So I'm saying at the point of intersection, the coordinates, the x coordinate and the y coordinate have to be the same. That's the only way you have the same point where they intersect, right? So that, what I'm trying to describe here is that they both have the same x coordinate and y coordinate. If that still doesn't make sense, I'm going to write it again. This means that x1 has to equal to x2. And this means y1 has to equal to y2. Because normally they're both two different equations. So they shouldn't have the same coordinates. But if they do have the same coordinates, it implies that they both intersect. That's the only way. It's like both of you meet at the same crossroad. That's why we're saying x1 equals x2 or y1 equals y2. We're saying only at this point of intersection will it work. This theory that I'm writing down right here, that I'm highlighting, that's what substitution method is. Okay, it only works because that theory is there. Because we know that they have to equal. Okay, so let's do an example now. So that was the theory. If you didn't understand the theory, you just learn the method. Okay, so this is what the Year 9 mainstream would do. They just learn the method. I describe the theory because as you move through, you need to think more laterally. Okay, at the moment, you're just learning the method, but eventually you have to think for yourselves and you have to think, what can I change? Yeah. So here, let's take this example. You got negative 2x minus 7, and you got y equals x plus 2. And again, let's go Desmos. So here we go. Let's visualize it. Y equals 2, negative 2x minus 7. I should really get sponsored. Maybe with enough YouTube videos, they'll pick up on me. And they're like, would you like this new upgraded program? All right. So what you see here is I just sketched those two equations. The green line is negative 2x minus 7. And the purple line is x plus 2, right? We can clearly see that these two graphs are going to intersect. How do I know? Different gradients. So both of them, m1 is equal to negative 2. m2 is clearly equal to 1. Even though we don't write it, there's a number in front of x. It's 1. It's not 0, because if it's 0, it's not there. Yeah? So I've got gradient 1, gradient 2, gradient m1, m2. Clearly, they're going to intersect because they have different gradients. So great, they're going to intersect. Number 2, here's the theory. If these two lines have different gradients, we know they intersect. That means at the point of intersection, both of them should share. Thanks, team. They should both have the same x and y coordinates. So both of them are two different equations right now. When you sub x in, there's a different y value. When you sub x in, there's a different y value. But at the point of intersection, so I'm going to write here, at point of intersection, they both share the same xy coordinates. So what I'm trying to say is x1 equals to x2 and y1 must equal to y2 because they both have to have the same coordinates. Now what's beautiful is these two equations are already written in y and y. This is your y1 right here. This is y1. This is your y2. And the only reason why you can do this next step, which is why all Year 9 students in the mainstream, when they first do it, they do this for everything. But it's not true for every time because not all graphs intersect. You only do it if you know they're going to intersect. And this is what they do. They memorize this step. Here's the next step. So the next step is, well, since this is y1, and we said that y1 needs to equal to y2, and this is y2, well, then I can rewrite it as negative 2x minus 7 is equal to 1x plus 2. So you'll find, I promise you, by the end of the year, if you go find a mainstream year 9, you ask them about it, they'll jump to this step straight away. They'll jump to this step straight away, and they do that for everything. They do it for all the time, but they don't know why they do this, okay? There is a reason why we do that. The reason why is because y1 equals y2, and that only occurs at the point of intersection. Nothing else, okay? So, let's have a look at this. I said that at the point of intersection, they both have the same y and x coordinates, so that means y1, instead of writing whatever the coordinates, which I don't know, but I do know that y1 is equal to this, and y2 equals that, but since they're both meant to equal each other, they're meant to be the same at the point of intersection, then that means these two x's are also the same. So that means you can collect them. They're the same terms, they're the same number. You can collect the terms. So here, back in year 8 and year 7, you learned how to solve this equation where you have two pronumerals on each side. That was one of the exercises. That's why I'm teaching my year 8s in term 3. But they don't see why we do that. We do that because we're teaching you how to do simultaneous equations for later on. That's what we're doing. So here, let's solve it. Collect the x's together. So I've got 1x over here, I've got negative 2x over there. And I taught you this at the start of the term as well. I said get the smaller x, and clearly negative 2 is smaller than 1. So I'm going to say plus 2x on the left, plus 2x on the right. Negative 2x plus 2x cancels out. You got negative 7 is equal to 3x plus 2. And you're back to linear equations that you're familiar with in year 7. Minus 2 on both sides. Negative 9 equals 3x. So I minus 2 on both sides. And then finally, x is equal to negative 3. Divide both sides by 3. And x equals to negative 3. Now you're not done. What does that tell me? What did you just work out? The x coordinate. But we're trying to find the point of intersection, so you need the y coordinate as well. So how do I find the y coordinate? That's it. And you choose whichever you want to put in. With my year 9s, they always get confused. They're like, which one do I sub it in? I'm like, either. Because they're both the same x's. I would sub it in the equation 2 because it's the easiest one to do. It would be negative 3 plus 2. Rather than timesing it by negative 2, then minus 7 is too confusing. So I would have just said, sub x equals negative 3 into y2. y2 equals now negative 3 plus 2. And that's negative 1. So what you just figured out is the point of intersection must be at negative 3, negative 1. So if I go back to Desmos and test that out, negative 3, negative 1, there it is. That's not by guessing. That was me doing a calculation that I said hypothetically they intersect. Y coordinates have to be the same. That's why you can equate the two equations. You just don't do that for the sake of doing it. The number of students who just equate things for the sake of equating is crazy. It's especially when you start doing it at a senior level, you get like 4 equations. You have to know which one you're doing with. So if you just equate things, it will be funny. All right? How's that feel so far? Make a bit more sense? Yes? So here's line 1. Line 1, line 2. Something like that. Negative 3, negative 1. All right. I want you to have a go with this one now. I'm going to pause the video. So, here we go. You have a choice of rearranging the equation back to what you were used to, if you like. I personally, because I know that y1 needs to equal to y2, x1 equals x2, I just need to rearrange to find out what y1 is, or y2, or x1, x2. It doesn't matter. So in my case, I would have done this one. This is just my own personal. I can see that to get y2, I just needed to move this across, which means add x2 on both sides. So if I add x2 on both sides, this cancels out. And what I get is negative 4 plus x2 is equal to y2. Now this is key because we said at the point of intersection y1 equals y2. So that means this y1 is equivalent to this y2. If that's true, I can just substitute this in. That's why it's called substitution method. Because I'm saying they're equal, you can replace it. Now if I replace it, my equation now becomes this, and it becomes much easier to solve. You got 3x1 plus, now this y1 is equal to y2, but y2 is equal to this. So you got negative 4 plus x2 is equal to 4. But remember what we said, x1 also equals to x2, so they're the same x's. You don't have to call them x1, y, x2 anymore, because they're exactly the same. So from here you can solve. 3x plus x is 4x, and that's a minus 4 there, is equal to 4. Add 4 on both sides. Get 8. Divide 4 on both sides. Hands up if you've got x coordinate equals to 2. Very good. You didn't have to do it my method. No matter which method you did, as long as you follow the theory, you should get x equals 2. If x equals 2, then according to this theory, y will then equal to negative 4 plus 2. It's negative 2. So you should have 2, negative 2 as your point of intersection. Let's test it. Desmos. There we go. There's my point of intersection. And that's because you know x1 equals x2, y1 equals y2. This is called substitution method because you have to rearrange and replace. Okay, that's why it's called substitution method. Yep. Now's the exercise from your textbook. Get some practice in. That's the theory. Next lesson I'll show you, Friday's lesson I'll show you elimination method.